Okay, let's begin. All right, so we're going to finish off the intro to the distributions, random variables today, and then get into the expected value and variance units, and see how deep we get into that. Anyway, the problem to kick off today is one, we could, okay, so many of you have solved this or a similar problem like this on your assignment, but here it is if you haven't done something like this before. So a computer program crashes within an hour with a probability of 2%, and every hour after that, okay, until it crashes. Okay, it's memoryless in that there's no accumulated damage to the program. It's always 2%, no matter what, no matter the fact that it's succeeded in not crashing the previous hours. What's the probability the program crashes within 24 hours? And you can draw a large probability tree for this, yeah? You could. And it would be 24 levels deep, right? So you would have, this would be a crash, and this would be not crashed, with a probability of 0.02, and then if it doesn't crash, then we go again. If it crashes, the program's dead, right? So it'll crash, and then we keep on going down like this, and we keep on basically tossing, metaphorical coins, has a probability of 2%, not very large, but still non-zero until you get down 24 levels deep. Okay, and you can figure out what the probability of it dying on the, the ith trial is, and then write a summation and add it all up. And, this sounds familiar, it's because you did it on one of your assignments. Okay, we're going to do the shortcut way today, and it's by introducing the final distribution that we haven't done, and that's the geometric distribution. So let's put this on hold for a moment. I'm going to draw this tree again on the geometric slide, but put the problem on hold, and we'll do it the fast way coming back. Okay, so what's a geometric distribution? Well, it is exactly a process just like we saw. A biased coin is tossed. Okay, it's always some sort of biased coin. It comes up heads with probability p, and you keep on tossing the coin until it comes up heads. Okay, you count the number of times you tossed. That is the value of the random variable, the number of times you tossed. Okay, so that's the way it's defined. A geometric random variable counts the number of trials until success. You can write a little computer program which has a while loop that I suppose in theory could run forever, but it tends not to. Okay, so you tend to get a resolution in a finite amount of time. Every time that you survive, you don't roll heads or toss of heads, you increment r by 1. And if you're to look at this as a probability tree, and it's always good to draw these things just to get context. On the first toss, with probability p, you get heads, and the whole thing ends. 1 minus p, you toss again, and you do the same thing, right? Probability p, you get heads, and you're done. Otherwise, you toss again. And you keep on doing this going down. Okay, so the tree itself is infinite, but the value of the random variable r here, the geometric random variable, is not infinite. Okay, so if you toss once, r is equal to 1 here, 2 here, 3 here, 4 here, and so on. Okay, so I sort of answered the first question, but I'm just going to ask it to you to make sure you're paying attention. What's the range for the geometric variable with parameter p? What value is going to take? Sorry? 1 to infinity, non-include. Can you just describe what's there? Good, yeah. So it's all the integers. Okay, so it's not a, it's not a dense set. That's the one you just gave me, was the closed real value interval. These are integers, so we tend to list them out. This is an infinite set, and it's maybe the first one of these that we've seen, but infinity is not an outcome, is not in the set. Okay, so it's not in the range. Okay, infinity is not a number that we toss around liberally. Okay, the PDF. Okay, so what's the probability that r is equal to x? Well, in order for us to get r is equal to x, first we have to toss 1 heads. It's going to be the last one. But we also have to toss, I guess, x minus 1 tails in advance, right? Okay, so it's got to be exactly that sequence. Tails, 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 followed by heads at the end on the xth trial. Okay, so in order to achieve r is equal to x, we must have x minus 1 failures and 1 success. And we can use the tools that we've got in our bag to analyze this. All the flips are independent. Okay, so we can define a sub I to be the the event the coin I was heads. Then the probability that r equals x is exactly the probability that the first coin a sub 1 was tails, and a sub 2 was tails, and a sub 3, and all of them, a sub x minus 1 was tails, and a sub x was heads. Just like all the others, the independence of this thing drops out. All these things are equal. All these are 1 minus p. And this one here is p. Okay, so I'm not going to write out an intermediate step. I think we can skip that, but if you feel like you need to, you go ahead. I'm not going to 1 minus p multiplied together x minus 1 times, so that's 1 minus p to the x minus 1 times p. Now, we're all computer people here, and so I'm going to point out something that's interesting to computer people. It might not be so interesting to other sorts of people that take probability courses, and this is that the geometric distribution has a nice property that you've seen before, all right? And the property is that the tree is actually recursive, okay? So this subtree is actually, the whole tree is just sort of shifted down by 1. Okay, and that's a really good observation to make as a computer scientist. You probably, oh yeah, it's sort of self-similar. And it's because it's mathematically self-similar, there are some tricks that we can employ when we get to geometric distribution in the next unit. So keep this in mind that this is kind of recursive here. Anyway, the CDF is, as usual, the sum of all the things that are to the left of x. So we'll do a little bit of math for this as well. Okay, so the CDF, R of x, is the sum of all these things. Okay, so the sum from I is equal to 1 to x. Well, I'm putting the floor in there just to be extra careful, but you know, it's okay if you don't. And so we're going to sub in this for I, so 1 minus p to the I minus 1 times p. And of all the things that are in there, you know, p doesn't actually have anything to do with I. Okay, so that's a common factor, and we can pull that thing out. But also, whatever is left inside here is 1 minus p to the, well, when I is equal to 1 is 1 minus p to the 0, and then when I is equal to 2 would be 1 minus p to the 1, and then to the 2, and then to the 3, and all the way up to x minus 1. Okay, so I'm just going to change the indices a little bit for our convenience. Okay, so I'm going to pull out the p, and I'm going to rewrite the sum as it goes from, I don't know, we'll just change indices to make it a little bit easier on us. Okay, from j equals 0 to x minus 1, 1 minus p to the j. Your midterm's in a week and a half. Let's see how prepared you are. What's this equal to? I have exactly 2 hands, and it's largely the same 2 hands that I tend to see for most of the classes in here. Okay, maybe it's better just to ask you, do you know what to do next? And I'll do it as a vote. And if you, you know, I don't want to embarrass anybody, but I just want to get a sense of how things are, okay? All right, so by show of hands, do you know what to do next with this? Okay, about 5 of you, 6, 7, 8 of you. Okay, well that's good, 8, 9, okay, we got 10. All right, maybe some of you are getting some recognition of this. And if you don't know what to do here, that's not good. Okay, this is one of the things that I started early in the course and said, you need to know this and commit it to memory. Okay? Yeah, okay, so you got to get on this. Okay, it's 10 days away. All right, 11 days away, sorry. All right, what do we do next? Somebody whose hand was up. Yep. Good, all right, so what should I write? P times? Well, that would be the infinite sum, yeah. So I agree it would be, if that x on the top there was infinity, then it would be 1 over 1 minus p. You would be absolutely right. Okay, let's write it out again. Okay, so a geometric series has the following, all right? So you have the sum from I equals 0 to, I guess, x of, what did I have? I had n, maybe. Okay, so from that to n of r to the I, what's that equal to? Yeah? Yeah, I don't have an a in yours. R to the n minus 1 over r minus 1. You're very close. You're very, very close. It's missing one thing. Yeah, it's r to the n plus 1. Okay, and it's okay if you write it backwards, like 1 minus r to the n plus 1, 1 minus r in the denominator. That's fine. Okay, so looking at this, okay, what should be here? Yeah, just do the math, right? All right. I'll do the math. That's fine. All right. So this is, all right, we'll plug it in. So we got x minus 1. That ones cancel out. So this is 1 minus p to the x minus 1 over 1 minus p minus 1. Maybe I should have written the 1 minus version over here. Anyway, 1 minus p minus 1 is minus p. Minus p cancels with this, but you end up getting a minus 1 in here. And the result is that you have 1 minus p to the x. Okay, so let's look at the distribution for a second. Okay, so this is a graph of the distribution for geometric of 0.2. The one that we're going to do on the next slide with the mean time to failure is 0.02. Okay, so it would have a slightly different thing, but it's curved downwards, sort of like 1 over 2 to the whatever. This value here is 0.2. All the other successive values are 0.8 of the previous value. So this should be 80% of the one that was above. That should be 80% of this one, and so on. And it will approach 0 as x goes to infinity. This is 1. Okay, so as you add all the things up, it should approach 1. And does that make sense for what's up here? It sure does. As x goes to infinity, this value here, 1 minus p, is, it's strictly less than 1, so it will tend to 0 as x tends to infinity. Okay, so as a sanity check, this all seems to work out, right? And these two curves are similar, right? We have this, multiplicative sort of, it's exponential, right? You're multiplying, it's a geometric series, I guess, but it's exponential decay, right? You're multiplying by 0.8 all the way through here, and this thing, if you flip it upside down, would have a similar curve to this. Okay, questions about the geometric distribution? Yeah, so as x tends to infinity, we're recalculating this for an infinite sum. Yep, that's right. And it converges to 1, right? Yeah, you can do the 1 over 1 minus r thing for the infinite geometric sum as well. If you look at what's going on in here, right, a ratio that is less than 1, you exponentiate that to infinity, it will turn into 0. So that's essentially what we're doing in this last step, is we're getting rid of that piece of the numerator. Yeah. This tilde means that this is the same distribution as the other thing. So it's like a congruent sign for distributions, basically. R behaves like, yeah. Okay, good. All right, let's do an example. Okay, mean time to failure. Okay, so the program is in this memoryless state. You keep on, testing, trying for up to 24 hours is what you want to sum the probability over. Okay, so let's set this up. Let's see the number of hours it takes until it crashes. Okay, C is a random variable. It has a range of 1, 2, 3, 4. Okay, it's unbounded. How do we write the distribution that C is similar to? Geometric of 0.02. Okay, so that's the probability that it will fail, and we're trying to figure out when it's going to fail. Now, we would like the probability that C is less than or equal to 24. How should we do it? How should we find this? Good. We want the CDF of 24. Okay, so what's the CDF formula? It's 1 over 1 minus, 1 minus p to the 24. Maybe I should just put p in there, save you a little writing. 0.02. Okay, and you can run this through your calculator. It ends up being 0.98 to the 24. Okay, that is a number slightly less than 1 that is exponentiated. Your calculator will handle this quite nicely and give you 38%. If you wanted to, if you didn't have a calculator available, you could approximate this thing out as e to the minus 0.02. It's always good to keep this in mind, exponentiate that to the 24. That combined will get you something that's around e to the minus a half. It's like minus 0.48. And that's a number that we've calculated a lot. Okay, so it's pretty close, just by taking these ballpark approximation. It's pretty close to the conjugate of 38. Would this be the same result as if you used reverse counting? Yeah, so I think so. Yeah, I think that's right. That makes sense, actually, because if it survives for 24 hours, that means it gets tails 24 times in a row. So yeah, so that's a really good observation. Yeah, so this is. This piece of the probability is no heads for X trials. And that sort of makes sense, right? That if you don't, if you get a heads in the first X, the opposite of that is you did not get one yet. Yeah, for the first time. So that's really good. Yeah, I like that. Yeah, and some of the independence exercises you're doing right now are tied into that. Yeah, I like that. I like that a lot. Thank you. Okay, other questions about this example or otherwise? Okay, these are the distributions. Nice. All right, so just to recap. Oops, that's not the right one. That's the right one. Okay, so we have explored 5 discrete distributions. These are the ones we're going to deal with the most. Bernoulli is a single coin toss, and uniform is a single die roll. These are things that we have built-in computer code to do. Others are sort of riffs off of that. Okay, so binomial is a bunch of coin tosses. The result is how many come up heads, total number come up heads. Geometric is a whole bunch of coin tosses, and it's the number of trials until you get your first heads. Okay, so time to failure, time to success, whatever it is, the first heads occurs. And Poisson is sort of a limiting case of the binomial, and we explored this thing last time. And under certain conditions, certain rare event conditions, where the average load is something close to a small integer or maybe a small fraction, and n and m, the number of things available, are large. So it's sort of like a limiting case for a discrete system. Anyway, it works well for large timescale rare events. Okay, so large n, small p, these things sort of cancel each other out. It ends up approximating binomial, and sometimes you end up with fractions like or exponentiation in your results that are really hard for your calculators to deal with. If you translate this into exponential space, okay, so you use Poisson, it ends up being easily calculable, which is great. I just want to mention a couple of continuous distributions because there is continuous statistics and it is studied by many, and there are 2 that are similar to the ones that are above. One is binomial, is similar to Gaussian. Okay, so whenever we're drawing these plots, we end up getting bell curves. Gaussian is the continuous version of that, and it ends up approximating a Gaussian in large case. The other one is exponential, and it looks exactly the same as a geometric distribution, except it's a continuous function. And these things, of course, in continuous land, instead of summing, you're using integration. So you have to make sure that the integration sums to 1. Anyway, that's a bunch of detail that you don't need to know for now. All right. I sort of talked a bit about the summary slide a little bit. I think I'm just going to use it as the first slide of the next unit. Okay, and the next unit is not stuff that's going to be on the midterm. Okay, but it will be on assignments 5 and 6. Okay, so this is, we got to keep going, right? We can't just stop. And the title here, expected value and variance, are 2 of the metrics that you're going to care about distributions going forward. Okay, so just as a teaser, and I brought this up at the end of last class, looking at these distributions, you're going to ask a lot of useful questions, like what is the average or the weighted average? And this is essentially asking where is it centered? Okay, so if you look at this binomial distribution, 20.7, which I keep on drawing for you, it is centered here. Okay, if you toss a weighted coin that's biased 0.7, you are going to get an average of 14 heads. Okay, so that it is centered here. And it sort of looks like the main meat of the thing is there, right? Where's the main meat? Variance asks sort of how wide the main bit is. Okay, so how wide is the main bit? And we'll just say, that's a pretty significant probability starting here. Okay, so plus or minus 4 is sort of the main bit. So from here to here, all of this stuff is the main bit. Okay, and most of this is what we consider to be likely. Okay, so how widespread is the main bit is what the variance is. Okay, how far away are the things? And the reason we ask ourselves that is so that if we look at these events here, so you look at the tail, okay, so anything that is outside the main bit is going to be really unlikely. Right? So you add up all these little probabilities, they're non-zero. Okay, so it's possible to get, but we want them to be rare. We don't want, we sort of expect that it's going to be near 14, plus or minus a little bit. Okay, so things that we would write for a tail inequality, we would write the probability that R is away from 14, which is its mean, plus or minus some value. And we use absolute value bars to get that job done. And we say the probability that R is 5 or less away from 14 is, say 95% or more. Okay, so you've heard of these things like we're 95% confident, right? You've heard these things, statistics, they talk about 95%, 98% confident. So this is the sort of thing that we're interested in going forward. Okay, so we will have tools by the end. You will have tools. And that's a little bit of foreshadowing. All right. This is a big packet, so we're going to spend a while on expectation. There's a lot there. We're going to spend a lot of time on variance. And the tail inequality stuff is actually in the unit that comes after this. Anyway, let's get started. Okay, so just to refresh your memory, where we just were, a random variable is simply a function that maps sample space onto some collection of real numbers. An indicator does a binary thing. Okay, and it partitions the sample space to events where you can see what maps onto each value in the range. And you can specify the probability distribution on top of that. Okay, so you basically assign a probability to each of the values in the range, and that would be the probability density function, or you can take a summation over the probability density function to get the cumulative distribution function. These things, you can have one or the other. Sometimes one is easier to get than the other, and you're getting to play a little bit with that on your current assignment, and we'll also get an opportunity on assignment 5 to do more of that. Okay, expectation. Okay, so what's expectation? It's a weighted average. That's all it is. Okay, so this, instead of summing all the probabilities, which would get us a 1, we are multiplying by the value in the range. So we're weighting it by the value in the range. Okay, so this summation of the things in the range is weighted by probability. Okay, I suspect you have done this sort of weighted average computation for many things, like computing your grades. Okay, so certain things are worth certain percentages. So it's sort of a weighted average, right? It has other names, okay, expected value, mean, or first moment. You're going to see all of these in your reference text, and I'll use these words from time to time. Okay, so let's dig into it. Standardized rolled. Its result is the random variable R. What's the expectation of R? Okay, so let's just look at, go from first principles here. So the range of R is 1 through 6. And the distribution is uniform. Okay, so the probability of any of the outcomes. Okay, so R is equal to 1, R is equal to 2, and so on. They're all the same, they're all a sixth. Okay, so just filling in the formula here, we are going to just apply the formula straight up. Okay, so the expectation of R is the sum, x in the range of R, x times the probability R is equal to x. And there are 6 things in the range. Okay, so we sub in x equals 1, and it has a probability of a sixth. And then we sub in x equals 2, and it has a probability of a sixth. And 3, that's a probability of a sixth. 4, also a probability of a sixth. 5, 6. And I'll pause here for just a moment to let you catch up. Okay, and hopefully your math instincts take over here and you see that there's a common factor of a sixth. Okay, and we're just adding the numbers 1 through 6, and that's 21, so 21 over 6 is 7 twelfths. Sorry, 7 halves, pardon me. 7 twelfths later. Which might be interesting, might be surprising. Maybe you already knew this about a standard die roll has an expected value of 3 halves. There's no 3.5 on the die, right? Okay, no 3.5. Okay, so your expectation doesn't necessarily need to be in the range. Okay, so a random variable, its expectation, don't necessarily have to overlap. Okay, it does not have to be part of the range. Okay, in general, for a uniform distribution where you're not necessarily rolling a die between 1 and n, okay, but you can have any collection of numbers that you wish. You have to compute the expected value. It's going to essentially add everything up. Okay, so it's just going to be a straight average. Okay, but just follow the formula. Okay, so this is x in the range of R, x times the probability that R is equal to x. And I could put in x is equal to v1 and x is equal to v2 and do all the substitutions. Okay, but there's one thing that we know here, right? And that's the probability that R is equal to x. What's that equal to? Sorry? 1 over n. Yeah, good. Okay, so this is 1 over n. Okay, so this is the sum, x in the range of R, x times 1 over n. And that 1 over n can get pulled out, so it's not dependent on x. Right, and it ends up just being the sum of all x divided by n. Sorry, I should have put 1 over n. 1 over n, sum of all x. Okay, and that's exactly what you expect an average to be. It's just adding up all the values. v1 plus v2 plus vn divided by n. Okay, so for the uniform case, that's sort of the classic average that you're used to. It is not really all that weighted, right? It's uniform. Everything has an equal chance. Okay, questions so far? Very good. All right, let's do another example. Lottery sells tickets with a 4-digit sequence, 0 through 9. And if you match all 4 digits that are drawn in the correct order, you win the grand prize. Second prize, 3 of the digits. Here, this is a redo or a part C of a problem that I think is back in Unit 2. Okay, and we're doing combinatorics. And here we're attaching prize money. Okay, so we're attaching some prize money. So if the grand prize wins 100,000 and the second prize is 500, what's the average win? Okay, so here we're actually doing something other than uniform, right? We're going to weight them by probability because, you know, the grand prize is not very likely and the second prize is also not very likely, but they're different probabilities, right? Okay, so we'll set up the problem as follows. We're going to let W be the amount 1. And there are 3 possibilities. There's either 100K, 500, or nothing. Okay, this formula, okay, so this formula in here, okay, we need probabilities. We have the values of X, right? There are 3 possibilities in the range. We need probabilities. We're going to get them from when we did this problem the first time. So the probability of a win was 1 over 10 to the 4th. Okay, I guess that's 1 over 10,000. And the probability of a second place finish is 0.36%. These are not very likely things, okay, but they're still non-zero probabilities. Anyway, we're going to weight them by those. Okay, so I'm just going to copy pasta that over. Okay, so the probability that W is 100,000 was 1 over 10 to the 4. And the probability that W is 500 was 36 over 10 to the 4. Then, okay, we're going to use the expected value formula. Okay, I'm just going to change pens just so that we can see it real clear. Okay, so the expected value of W is all x's in the range of W, x times the probability that W is equal to x. And there are 3 things to do. Okay, 100,000 times 1 over 10 to the 4. 500, 36 over 10 to the 4. And 0 times, I don't know that we care, right? We're multiplying by 0. This is actually a really nice thing for having an outcome of 0, right? Because it makes the multiplication easy. If you want to compute the probability that W is equal to 0, you can do it. It's 1 minus 1 over 10 to the 4th and 36 over 10 to the 4th. Or you could just write, you know, you could instead write this as the probability that W is equal to 0 and not care because the big red marker is coming to get you, right? Okay, well, the numbers are mercifully nice here because this divides this exactly, and that's 10. And this doesn't divide it exactly, but it's close. It's actually $1.80. Okay, so this is $10, and this is $1.80, so we end up getting $11.80. Okay, questions about this? A lot of you play games. I play games. I play the lottery. I bought a lottery ticket today. You've looked at the lottery problem a little bit. If you were to structure a lottery like this, if you were the government or the casino that was putting this thing on, this is an interesting thing, right? You would need to make this calculation in advance and say, okay, well, each ticket has got to be probably a lot more than $11.80 in order for us to make money off of this, right? Okay, so I don't know what you would sell it for, $20, $25, to make sure that you make enough money. There's also some administrative charges in handling lotteries. Okay, so, but you would have to pick a number that's bigger than $11.80, otherwise you're guaranteed to lose money. Okay, casinos make similar computations when they choose their games, and so I'm just going to talk a little bit about probability versus odds, because when you're in the gaming world, and some of you are, you hear like odds, right? And when people talk to you, sort of, you know, off the cuff, they might say one of 2 things to you, right? And I've used one particular set of language during this course, and that is, you know, if I say the chances are, okay, so the chances are of some event X occurring are 1 in 1,000. That is a probability, okay, that represents 0.1%. But other people might say your odds are 1,000 to 1, okay? And that sounds similar, but they are 2 slightly different things, okay? So what's the subtle difference here? Okay, the first one describes a probability, okay? So it's your success rate versus all the possibilities, 1 over 1,000. The second describes a ratio, and it's the ratio of bad things, okay, fail cases versus success cases. Okay, so when you say 1,000 to 1, there are actually 1,001 cases. Okay, so there's 1,001 outcomes. 1,000 of them are bad, and 1 of them is good. Okay, so your probability is actually 1 over 1,001 in that case, which is just slightly different than 1 over 1,000. I grant that these things are pretty close, but they are not the same thing. Okay, so if you wanted an equivalent thing, you would say 999 to 1 is your odds. Okay, people use odds in 2 different places quite frequently. That's said colloquially a lot, like you're 1 to 1, right? That means you're even money or you're even odds. People say this. Okay, so even money. This is a coin flip. Okay, so you're 50% even odds. You're 1 to 1. But usually you'll see odds in 2 places. You'll see them at the racetrack for horses as you're betting. They'll show you the live odds, or when you're doing sports betting. Okay, so I'm going to show you both of these, and I have probably enough time for both today. Okay, so the first one is horse racing. Okay, so if you bet on a horse that's 4 to 1 odds, that means that your payout on a bet is like on a $1 bet, say. So this 1 here will be 4 times whatever your bet was, so $4. Okay, so you will be plus $4. So that means you will get $5 back for your ticket, or you'll get nothing back for your ticket. Okay, so a question about whether you should bet on a horse that you believe is going to win with 4 to 1 odds is an expected value computation as follows. Okay, so if W is the expected win, we want the expected value of W to be greater than $1 for us to put our dollar in jeopardy. All right, and so this thing here, if we translate that using our expected value formula, there are 2 outcomes. Either the horse wins with probability P, and you get $5, that's your value. Okay, so 5 times P, or you get nothing with the chances of 1 minus P. And again, multiplying by nothing is maybe a little bit, you might just not pay attention to that, but you want that value to be greater than 1. So you compute this, and that means that P has got to be at least 0.2, 20%. Okay, so if you think the horse has a 20% or greater chance to win, then you make the bet, and you should see a positive expectation. You expect to win money off that bet. Yeah? Yep. Yeah, you can do that as well. So you can talk about your expected profit or expected loss, and you can say 4 times P, and then it'll be minus 1 times 1 minus P. I was going to do that calculation for, yeah, you'll get the same thing. I was going to do that calculation for the second one we do here, the sports betting. And probably I don't have enough time to do that. So maybe I'll save that. But yeah, hold that thought for, thanks for the question, hold that thought for Wednesday. So I'll do that exact version on Wednesday's class. Yeah. Time for a couple questions though. Yeah. Yeah, so that's a good way of thinking about it. Yeah, so this is 4 to 1 odds. These are the bad cases versus the good cases, right? So you can do that mental computation as well, and you can say there's 1 good case out of 5 total cases and get probability at 0.2. It's the exact same thing. It's supposed to, how is that different than the P is the question. It's supposed to represent the P, but in a betting sort of fashion. So you can please don't do that. It's really, okay, there's somebody asking a question, and that's really rude to them, and it's really rude to me who's trying to answer the question. Like, can you just, like, the class is not even over, right? So don't do that. How can P be more than 0.2? Well, you might believe that the horse has a better chance than what the stated odds are, right? So for every $1 that you put in, you're getting 4 back, right? Multiplied by whatever probability that the horse actually has.